I am different than all of you other lecturers so far in that I'm an experimentalist. So it's a little bit daunting to come before the theory audience and be the only experimental representative, but okay. One thing I want to emphasize here is that if you have any questions, I am trying to hit the highlights of what I think is important for you to know as theorists, as theory students, and beyond. For the LHC, these are things that relate to the limitations of the machine, why the machine is designed in a certain way, why the experiments are designed and run in certain ways, so that whenever you hear the results coming out from the machine, even starting, well, last few weeks, there have already been conference results at the physics at the LHC conference in Hamburg. You'll know how to interpret those results, or you'll know why things were done a certain way, why things weren't done, just as importantly, a certain way. And I'm also trying to help build the bridge so that you can see what things still need to be worked on from the theory side as far as the experiments go. And I think Matt may also talk some about that in his theory at the LHC lectures that he's giving concurrently. So we've been trying pretty hard to minimize the overlaps and make sure that the groundwork that's laid in one lecture gets carried on onto the next lecture. So we'll continue that for the next 5 days. Some people were trying to guess which experiment I'm from. I'm from the Atlas experiment, but I can see we have lots of representatives in the audience from the CMS experiment. Welcome. From a local Boulder contingent. Okay, I'm going to use the screen, but also the blackboard. And the reason that I'm going to use the screen is that we're taught, and I teach all my students to make plots as their way of proving that work is actually being done. Okay, so instead of just giving you a whole bunch of words about what could be done or might be done, the plots are intended to show what is being done and what we actually know. So I'll be trying to use both. Like I said, I'm trying to focus on what you really need to know. These are the outlines for the 5 lectures. If anybody has something specific that they really would like to hear about, come up and give me feedback, and we'll see if there's a chance to work it in. Some of the things in the last lecture may be a little bit subject to change. So the idea is we're going to start today talking about how the LHC was designed, and in some sense talking about the inevitability of the way the LHC is designed and the way it operates. Then I'll talk about the detectors, especially the design and the physics of the electronic detectors next time, tomorrow, including some particle reconstruction. The idea behind this is that I think you'll find that there are lots of exotic physics beyond the standard model that have certain signatures in the detectors that are not what people are used to. But if you know how the detectors work and you know what the physics is of the interactions of the particles with the material, you'll be able to predict these new and striking signatures whenever you build your new model. And that's a very powerful thing because experimentalists really like to be told what to look for exactly, believe it or not. So I'll give some examples tomorrow about new models that people have that really are new signatures. A little bit different from what we'll be talking about later in the week, just showing how the physics that we learn tomorrow will be directly applicable to new physics. I'll be talking about the hadronic jet physics. If I could leave one message with you, it's that you remember those cross-sections that Matt was showing this morning, Matt Strassler was showing this morning, showing that we're orders of magnitude, 12 orders of magnitude down in the physics processes we're looking for compared to what the dominant cross-sections are. It helps to look for things like leptons, electrons, muons, taus, but you can't really get away from all the jets that will be present in the Hadron Collider. And so I think it's important to talk a little bit about this hadronic jet physics, and that is one place where there's been a very strong interplay between the theory and experiment. So I want to show that to you in particular. And then later in the week, we'll be talking about how to look for new physics and some of the techniques that experimentalists use for that. So I've been aided by talking with the theorists at Santa Cruz, too, and trying to understand what their ideas of experiment are and also their misconceptions. Okay, so we'll start by going back to the lectures that we had this morning. So you remember in Matt Strassler's lectures, he motivated the idea of new physics at the terascale, at the 1 TeV scale. So if you knew that there was physics at the 1 TeV scale, how would you go about looking for it? Well, one way that you would go about looking for it, you say a TeV. What does it really mean to reach that TeV scale? It means that, well, there are 2 ways to look for new physics. One is to look in precision physics for effects of new particles that might come in through loops. So I think that you might have seen this morning some diagrams showing what might happen if you have new physics loops. So let's say, for example, that you have, I'm going to think about boy, it's a nice shiny chalkboard here. So Matt talked about what happens with the Higgs. So one thing you can consider is if you have the standard model particles that are coupling to the Higgs like this. Okay, so modifications to the Higgs through these couplings. You could also have, instead of the W, some new particles, and anything that would couple to the Higgs, for example, would be a good candidate here. I don't know, we could put top in here. It certainly couples to the Higgs, but that's not a new particle. Let's think about some new sparticle. So I'll just make it a sparticle like that. It's not supposed to be a supersymmetric proton, but let me just call it a generic particle. Okay. So this is an example of a loop contribution that you might see if you were able to do some precision electroweak physics, and you might be able to, well, actually, if you were able to measure the Higgs mass, then you would be able to infer the existence of these new particles. What we're probably more interested in as experimentalists is actually producing these particles and seeing them on shell instead of the virtual particles. So in order to do that, we really need to reach a momentum scatter, a q squared of 1 TeV squared. And the only way really to do that is to have a collider that's at that TeV scale. So we have a bunch of options for colliders that could be at that TeV scale. One of them is not a collider, but a beam on a fixed target. So if you had a very, very energetic beam on a fixed target, you could potentially have a center of mass energy that would be close to 1 TeV. But if you actually work out what energy beam you need for this, it's an enormous energy. And the reason is that most of the energy that would go instead of the energy going into the momentum transfer here between the beam and the target, you actually have a center of mass that is boosted in this direction with the beam. And so it turns out that the energy that you get in this case, the energy of the center of mass, really is only the square root of the beam energy and the target mass. So this is not really a very efficient way to get up to 1 TeV. So your other alternatives are to look for a collider instead. And if you have a symmetric collider where you have equal energies here in the beams, then you have a center of mass energy that, instead of being the square root of that beam energy, even if it's twice the square root, but anyway, proportional to the square root, actually just ends up being twice the beam energy. Okay. So if you can manage to build a collider, you will make it a lot easier to get yourself up to 1 TeV. In fact, that's really the only practical way to get 1 TeV. The fixed target experiments really won't get you up to 1 TeV, except if you wait for a very high energy cosmic ray, and those only happen, once a year, once every couple of years. So you certainly won't have the rate of collisions that you need. So on the collider front, you have two choices. You can look at a Hadron Collider, or you can look at a lepton collider. And I'll make the argument that the lepton collider has some limitations that are technological and geographical and political limitations. The Hadron Collider has been our best bet, and that's why the LHC is our Hadron Collider. The lepton collider, it turns out, you have two choices for a lepton collider, actually any collider in general. I've drawn a linear collider here where the beams are going like this, but in fact you could also have a circular collider where the beams are counter-rotating. Actually, let me draw them like this. Counter-rotating beams that collide at certain interaction points. The drawback to these sort of circular colliders is that, especially if you have the very low mass particles like electrons, is you have a significant amount of synchrotron radiation. So I'm sure everyone remembers their favorite course in graduate school, which is classical electrodynamics. So these equations might be familiar to you. Actually, I think I took these out of the undergraduate. This is just the power radiated by a charge as it's accelerated. And if the particles are going in a circle, traveling in a circle, and the acceleration is the force needed to keep it moving in a circle, then it transforms to that formula there where rho is the radius of curvature. So rho is the radius that you have here in the collider. This is rho. So you have two choices. Either you can make the radius of curvature very, very large, basically infinite, and that would reduce the power here. Or you could go to a more massive particle. And the reason that going to a more massive particle helps is because of the gamma factor up there. So you remember that the gamma is approximately the E over m. So if you're able to switch particles, and instead of going to the electrons, go to something else like muons or protons or something else that's accelerating in a circle, then you win. Just to give you an example about what a problem this is, at the LEP collider, the electrons, this was the highest energy electron-positron collider ever, and the electrons there were radiating about 0.1 microwatts per electron. And that might not sound like a lot, but if you consider that there was 1.5 milliamps in the beam, then you have a large number of electrons, so a large fraction of the power that was being pumped into the collider was just to overcome the synchrotron losses. And that's what we're trying to avoid with the proton collider. So let's put electrons aside and say that in the collider anyway, in the circular collider, the electrons won't work. What could we do instead? Well, we could do one of two things. We definitely have to have stable particles to be in the collider. So protons, we're pretty much limited to protons and electrons, stable charged particles. People have proposed using muons, but the problem with muons is that they decay. They're not exactly stable. They're stable, I would say, mesoscopically, but not on a macroscopic time scale, not on a long time scale. So we're really left with protons and electrons. And as we said, the electrons will radiate. So one possible solution for the electrons is to have a linear accelerator. And some people may be saying, yes, I know all this. Well, I'm trying to take us back through what all the considerations were, why the LHC is kind of the inevitable machine for this day and age. Okay. So if you wanted to figure out how to get to the TeV scale, you have to decide how to accelerate the beams up to a TeV scale. And remember, we're still talking about either a linear or a circular collider. But we know it has to be a collider, not this fixed target experiment. So if you go back and look at the radio frequency cavities that are available for acceleration, we'll talk a little bit more about how those particles are accelerated. But for right now, know that the key number here is the acceleration gradient. That is what energy goes into each electron or goes into each charged particle per meter. So at LEP, you see that the acceleration gradient was 7.5 megavolts per meter. At SLAC, which was the largest linear collider, it was quite a bit higher at a higher frequency, but 20 megavolts per meter. And if you try to plug these numbers into a 1 TeV beam, or a 1 TeV collider, which would be a 500 on 500 GeV beam, you come up with a distance that's something like 25 kilometers for a linear accelerator. So in order to reach your 1 TeV accelerator, that's what you would need if it were a linear accelerator. And in fact, people have proposed exactly this accelerator. I'm sure you know about these plans for the ILC, the global design effort for the ILC. And ILC is trying to make sure that the cavities will reach at least 30 megavolts per meter, which is a little bit higher than these SLC-RF gradients, but using a fundamentally different technology, using the technology that corresponds to those LEP superconducting cavities. So this picture that's here up on the right is a picture of one of the cavities that's proposed for the ILC. These are superconducting niobium cavities. They are cavities that have niobium spun on the inner surfaces, and then they're electroplated to try to avoid any critical field problems. But as it is now, we think that the 1 TeV E plus E minus machine will have to wait. That's, of course, the ILC. Even though a lot of work is going towards qualifying these cavities, we know that the ILC is not built yet. So people decided to look instead at the circular colliders again. So now we've kind of narrowed things down. We're at a circular collider. We believe we can build a circular collider with the only stable particle that's left to us, which is the proton. We said the electrons would radiate too much synchrotron radiation to make them useful. So how do we figure out how to really build this thing? What energy can we really get out of this machine? We say 1 TeV, but how do we get up to 1 TeV? you saw from Matt's talk this morning that not all the energy of the proton will be available to the collision, because what we're really colliding are not the protons themselves, but the constituents. So that means we want to be substantially above 1 TeV, and the question is how much above 1 TeV we can possibly be. So in order to do this, we look at the force that's needed for the acceleration. If you just plug in the Lorentz force and try to calculate what's the circular acceleration that you get from the Lorentz force, in the non-relativistic case, you have this formula, rho equals P over QB. I'm sure that people have worked that out before. And it turns out that this gives you the cyclotron frequency. So the cyclotron frequency is at what frequency do you have to kick the particles as they are, what is the frequency that you need to pump in for acceleration for these particles to keep them moving in that radius that you've picked. In the relativistic case, it has another factor of gamma that's added to it because of the way that the velocity changes, the proper time changes. And you have a choice now. You can choose to either ramp up the magnetic field as the frequency changes from being a very high frequency at the injection to a lower frequency as you move along. That's what happens in the relativistic case. Because the gamma is changing, you don't have any more a static frequency. In the old days, people would really increase the B field as you increase the gamma of the particles. So increasing the B field is good instead of increasing the frequency as it goes around. Oops, I said that backwards. In the old days, you had a fixed B field, right? So you would actually increase the frequency as you go along. But here, we're choosing instead to vary the B field, that is the magnets that are providing the bending power around the ring, instead of the frequency. So let me give you an idea what I mean. So let's say this is our collider here. Now, in order to generate the bending power as it goes along, we might put magnets all around this ring here, okay? And what's important here is the integrated B field as you go along the ring that provides the bending field, all these magnets, to provide all the integrated B field, the force that you need in order to go around the ring. And in fact, that's what's chosen to be done for all of these large synchrocyclotrons, and including the tevatron, including LHC. So you're limited in some fact over what range you can vary the B field. You might start out with a low B field, and then as the particles are accelerated faster and faster, you have to increase the B field. You're limited on the high end, we'll talk about in a second, by the superconducting magnet technology. Let me say what the units are, so you can do some handy calculations on your own here. If you take pretty normal units, this would just be an exercise if none of you have done it already. If you take normal units for the P, the momentum, so in GeV, or GeV over C if you prefer, and the B field in Tesla, and then rho in meters. Be careful that it's in meters, not in kilometers. That can always throw you off. Then this equation holds. The 0.3 is just the conversion factors for the MKS units compared to the formula that we have up there on the top. So if you want to figure out what radius of curvature is needed or what magnetic field is needed for a given radius of curvature, then you can use this formula to figure that out. So you might take the tevatron as an example. Tevatron was the largest collider operating a few years ago. And the tevatron has a radius of 1 kilometer, has a beam energy of 960 GeV. This is the tevatron run 2. And so if you work that out, you get a B field that's about 3 Tesla. So that 3 Tesla is just past the limits of what conventional magnets can do. We'll see on the next slide. Now the problem is it's difficult to increase B, because I'll show you that the superconducting magnet technology kind of limits you to around 8 Tesla, or just above 8 Tesla, maybe around 10 Tesla. It's hard to increase rho, because an increase in rho means you have to build a bigger ring, which means you have to put more magnets in the ring or build a bigger tunnel or something like that. So the limits there are not only, they're not physics, but they're really geographical and political and financial about how big you can build that ring. Now I would argue that What we'd like to have if we want to reach the 1 TeV scale, for reasons that Matt will mention tomorrow, actually, when he comes to talk about parton distribution functions, is that you'd like to have something that is about, I would say, 10 times, or 7 to 10 times higher than the scale that you want to reach. And the reason for that is if you look at the proton distribution functions inside the proton, here I'll steal a little bit of thunder here. If you have a fractional, if you have some fraction of the proton momentum, we'll call that x, and you have some probability to have the certain x. If you look at the U quarks, for example, inside the proton, there's a shoulder here. And so it's steeply falling as you get up to an x, and this is right in the range around 0.1. Okay. So when you get down to about 1/10 of the beam energy, you have a nice shoulder there where you have access to the U quarks. So being up here is a little bit too ambitious. Being down here won't get you to 1 TeV, but being around the 10 or 15% level is just the sweet spot. Well, that was actually 4 or the beam was 4. So if you have 3.5, I think that most people will say that it's not quite what they would have hoped to get to the terascale. In fact, I didn't expect you to ask that question. I expected maybe someone older to ask the question, because you might remember that about, 15 years ago, I guess when I was an undergrad, the SSC was proposed. And the SSC would have been even higher energy than the LHC. So there was some debate about whether the LHC even was high enough energy at that time. So the only way to know is to actually do the work and try to calculate the cross sections in the way that you'll see tomorrow, and decide whether the rate is high enough to give you what you want for the rare processes that you're looking for. That's really the only way. Okay. But that's why the LHC wasn't designed for 7 TeV. Okay. Or 7 TeV total energy. So the question is, how big can it be? And the answer is basically how big are you willing to build your ring? Now, in the case of the CERN Large Hadron Collider, it turns out that there was already a ring that was built. And technically, it wasn't a ring, it was an octagon. The reason it was an octagon is because, remember, it was using electrons. So since it was using electrons, it was decided to try to minimize the curvature. So in other words, there were accelerating sections that were straight, and then there were a few bends. So I guess there were bends that look like this. Right? So the whole thing is just one big octagon. Hope I'm drawing an octagon here. Okay. Poor man's octagon. At least the sides count up, right? Okay. So this octagon could be reused. The tunnel was already built. We'll see in a second. There was just one little problem with the tunnel, though. Yes?
Do we really reduce the curvature? Because it seems that at each junction, we have really big.
That's exactly right. So the advantage is that you're limiting the places where you have the curvature. So you're limiting the places where you have the loss due to the synchrotron radiation. And what you would like is you'd like to have the collisions happen somewhere in the middle here, when you have a chance to make up the energy that was lost in the synchrotron collisions. And in fact, that's exactly how LEP worked, is that the interaction points were in the middle of these accelerating regions. Okay, so they were made sure that the beams were brought up to the full energy, even though they had synchrotron radiation losses. Okay. This is actually an important point, because it means that the ring that LHC is in still maintains the same shape, even though now it's a proton-proton collider, and there's no reason to have this geometry like this. That's still the ring that's built. So that's what's actually used. It doesn't really make any difference for the physics, but it makes sense from the point of view of history. This is not how you would necessarily design it, but from the point of view of history, if it's already built, then you use it. Okay, the other thing that's different, I'm glad you brought up that point, is that at LEP, at this electron-positron collider, the collisions happened in these equidistant interaction points here. So the beams were brought to collision at these 4 points. It's changed for the LHC. And for the LHC, we'll see on the next page, there are only certain points, actually the places where the collisions happen are changed fundamentally. So the proton beams are brought into collision at different points. Okay, let me just show you that. This is what the LHC ring, or as we know now, pseudo ring looks like. The points where the beams are brought into collision are these points at 0.5, which is the favorite point for people working on the CMS experiment, 0.1 for the Atlas experiment, 0.2 for the ALICE experiment, and 0.8 for LHCb. So the other points are just access for the ring there. Okay. It turns out that the RF acceleration for the LHC is up there at 0.4, which is why 0.4. Well, 0.4 is large on the map because there used to be an experiment there. And also 0.6 is large on the map because there used to be an experiment there. Okay, but this gives you some idea of the infrastructure. You see that there is a feeder ring here, an injector ring called the SPS. That is actually the last ring where the protons are before they get injected into the LHC. And you can see the injection tunnels that go from the SPS. I mean, everything in the SPS is rotating clockwise here, as we see in this photo. So the transfer tunnel for one ring goes down this way. I'll show this one. This one right here. And then the other one is this one here. Okay, so far we have basically, yes, go back.
Why did they change the interaction points?
Yeah, that's actually a good question. So one reason that they changed the interaction points was to build the bigger caverns for the bigger experiments. So CMS and Atlas were substantially bigger experiments than they had in any of the other caverns. And so my understanding is that they wanted to redo and build those caverns using the engineering techniques that they didn't have whenever they built those other caverns there. So the caverns that, well, the ALICE experiment stays in 0.2 because it's using a magnet that was already there in 0.2, and people did not want to move that. And the LHCb experiment is taking over one of the old access points. Yeah, for 0.5 and 0.1, I think that's the reason. But that's a good question. I'll have to check that out for sure. Okay, so we have set basically the radius of curvature. And if you go back to our equation now, we've set what we want for the P, for the beam energy. We've set what we can have for the rho, the radius of curvature. And so now we just need to look up in our formula what we need for the B fields. And the question is, what can we get? What energy beams can we really get?
Quick question.
Yes?
So between the points, the tube is straight,
Mm-hmm.
so we don't need to apply a bending field?
That's a great question.
And then it's just a... Okay.
Exactly. So that's actually what I have written here. If you look at that total bending field, that B that's in that equation there with the 0.3 B rho, that's the average field that you would have if you had a constant force, constant Lorentz force, providing the circular acceleration on average. Okay, so that's why if you plug in the numbers for the LHC magnets and the LHC beams and the LHC radius, it doesn't satisfy that formula that I gave you. And the reason is that the bending field is not constant all the way around the ring. Okay. In fact, you can see it here, what exactly the difference is. The dipoles don't completely line the LHC ring because of the geometry that we just talked about in part. So really, it's about 60% of the ring is loaded with those dipoles. So you can do the calculations. You plug in some numbers. For the design beam energy, or the maximum beam energy of 7 TeV, you get a peak dipole energy of 8.3 Tesla. And for the current running geometry, or the current running energy of 3.5 TeV per beam, that's a magnetic field, and a peak magnetic field of 4.2 Tesla. So you might say, well, let's up the voltage. Up the voltage and let's have a higher magnetic field. Well, there are actually problems with that, and that has to do with the magnet technology. The conventional ferromagnets, those of you who are working on superconductors might know about this. You can only have so much, you can only have such a strong magnetic field before all the domains in the ferromagnet are all pointing in the same direction. Okay? Once you have all the domains pointing in the same direction of the ferromagnet, you're done. There's nothing more you can do. You can't really This is called the domain saturation. So effectively, this limits what you can have in a conventional electromagnet to about 2 Tesla. Now, you can do a little bit better with the superconducting magnets, in fact, a lot better. As far as I know, the highest field that's been achieved with superconducting magnets is, I think, around 100 Tesla. But unfortunately, that's a destructive measurement. So basically, the magnet has to be imploding while it happens, which is not very useful for our accelerators. Okay? The best that we can do for these stable magnets is around 10 Tesla. And so the LHC is kind of pushing it with the 8.3 Tesla, the large dipoles, and the very high fields. And this is basically limited by the forces that you have inside the cable. The way that the superconducting magnets work for the LHC, of course, they're wound, but they're not wound with regular wire like an electromagnet would be. They're wound with superconducting cables. Let me erase this here. And the superconducting cables are filaments of superconductor that are embedded somehow in a metallic matrix. So if you look at the pictures, it's these filaments that are lined up in here. Not exactly in this configuration, but this will give you the idea. So basically how this is done is the wires are packed inside a matrix, and then the whole thing is drawn out to a very fine cable size, and the filaments inside get finer and finer. But nevertheless, you have forces that are acting between the consecutive turns of this cable on the magnets, and possibly even between the filaments themselves. Okay, so these are the niobium cables, the Rutherford cables that I mentioned up above. And this is what all the superconducting magnets use in all of these colliders. Okay, so now we have basically fixed what the scale will be for the collider in terms of the radius of curvature, in terms of the magnetic field, and that fixes what beam energy we can have. So we can say our design energy is 7 TeV per beam. That's what we need. Now, in order to access the 1 TeV scale with a 7 TeV per beam, or 3.5 TeV per beam, let's say 7 TeV per beam, you need a very high intensity beam. And the reason is that even though it happens that you have the 1 TeV of q squared momentum transfer between 7 TeV beams, it doesn't happen often, or I should say it happens with some probability. Okay? If you're looking for things that are even beyond 1 TeV, which we are with LHC, then you have to have a very intense beam that increases the probability for these rare processes to happen. So you heard from the lectures this morning that the cross sections are 1 in 10 to the 12 compared to the rate of collisions that we expect from ordinary proton-on-proton collisions. But if you are able to increase the intensity and increase the total number of collisions, then even a low rate like that will still give you a significant number of events. And that's exactly what we're looking for. So once we've defined the beam energy, we might be forced to conclude that we need a very intense beam. And the answer to how intense it has to be is a delicate dance between the experimentalists who are trying to analyze the data for these rare processes and the accelerator physicists who are trying to build a safe machine with beams that aren't too intense and beams that won't rip each other apart. We'll talk about that in a second. So the answer depends on a lot of things. What can be done from the accelerator side and what the experimentalists would like to have done from the experimental side. So let's start with some numbers here. So the low interaction rates for the rare processes, these are processes that would be at the TeV scale or above, basically require, people found after study, they require an instantaneous luminosity of 1 times 10 to the 34 per, this is particles per centimeter squared per second. Okay, so that's the number of particles passing through. Well, I should say that's the instantaneous luminosity. So let me say a little bit more about that. The instantaneous luminosity, the luminosity, it's very much related to the cross sections that you heard at the beginning of the lecture this morning. And let's say a few more words about those, actually. Let me write down this 10 to the 34. So 1e34 per centimeter squared per second. Okay. So this sounds like what we would call a flux, right? A particle flux. particle flux is number of particles going through some area in some time. Okay? Oh, I guess I should say that how it compares with the other colliders. So the peak tevatron instantaneous luminosity was, you can see, a factor of, what's that? A factor of 25 lower than the instantaneous luminosity for the LHC. So we're not only increasing the energy, a factor of 3.5 above the tevatron energy, but we're also increasing the intensity by a factor of 25. So now you see why this is such an ambitious machine. So with the current parameters, that is taking into account how many electrons or how many protons will speed through per second, and taking into account the size of the beam, this corresponds to about 3 times 10 to the 14 protons in each beam. Okay, so you could get some estimate from this as an exercise about how big the beams are, if this translates into 1 times 10 to the 34 per centimeter squared. Okay, so these are the number of protons that we need in the beam. That is a lot of protons. How many protons is it exactly? So you might notice that I've been talking about LHC as a proton collider, but you might ask the question, why not anti-protons? Why does it have to be a proton-proton collider? In fact, there are some reasons that it would be nicer to have it to be a proton-anti-proton collider instead. You saw this morning the Feynman diagram for the W production. So I'm going to use a D and a U bar, making a W. So it actually makes a W minus. If you had an anti-proton proton collider, then you'd be colliding your P, which has UUD, plus we saw other things, right? Gluons, all the other quarks inside. On P bar, which has U bar, D bar. Okay. So notice that instead of having to rely on the other things that are in here, remember the D bar was in here along with U bars. In this one, we would have U and D, and we'll hear more about that tomorrow. But instead of having to worry about those, we would be able to access directly the U bar that was in the anti-proton. So this is a little bit easier than having to rely on these other quarks that are floating around, or that are the virtual quarks, if you like, and virtual partons inside the proton. Okay, why don't we do that? The reason is that if we look at our design target, we said in order to access the physics that we want, we need a very intense proton beam. Okay? So with 3 times 10 to the 14 protons total in each beam, you might think, well, let's try to have 3 times 10 to the 14 antiprotons in the other beam. And then we can have a P bar, proton-antiproton collider. That would be nice as far as the physics goes. The problem is that making and accumulating these antiprotons is very hard. The Tevatron collider, which still is a PP bar collider, has so far managed to accumulate, or to max out the accumulation rate for antiprotons at 10 billion per hour. Actually 30 billion per hour. So that is a lot. That's the result of years of work, basically 25 years of antiproton accumulation work. But we need something more than that. I mean, we're looking for something that would be factors of 100 above that. The maximum number of antiprotons in the Tevatron beam are 3 times 10 to the 12. And in fact, we want much more than that. Question?
So it seems like another way to try and sort of increase what effectively is the luminosity would be if you could somehow focus the beams better. Is that just a complete non-starter?
No, that's a very good question. We'll actually see later on in this lecture about how there's a fundamental limitation on how far the beams can be squeezed. The basic thing is if you have a lot of protons, they can't all be squeezed together too tightly, otherwise they'll interact with each other and blow the beam up. Question? Well, we will come to the conclusion that we'll have proton beams in the opposite directions, right? This is the consideration of having proton in opposite directions or proton-antiproton in opposite directions. But you're right, they're definitely in opposite directions. Okay.
Then you would need the magnetic fields for the two beams in the output.
Exactly right. If I could rephrase your question, if you have 2 proton beams, they can't use the same magnets, right?
Yeah, I mean,
They can't be using the same magnetic bending field. Exactly. That is a great question. We'll get to that in the next couple slides. Okay? Question here. Can you win something by that? That's true. So, in fact, you might say, well, maybe if I used antiprotons instead, I wouldn't have to have such an intense beam. I could have a slightly lower luminosity, a slightly smaller luminosity, and I could still do the physics that I want to do. So that's exactly the kind of studies that were done, and then people came to the conclusion that the proton-proton would be the best. It's hard to give some back-of-the-envelope calculation about what would be the best. It really involves doing a study. So, but it's a great question. That's the way to think. That's what I'm hoping to get across in these lectures, is that all of these things didn't just come handed down, but someone actually did the studies and drew these conclusions.
What is actually the difference in the carbonization functions of these high energies between protons and conductors?
Oh, well, one of the big differences is what the valence quarks are.
I'll show pictures
Right.
tomorrow.
Matt will show them tomorrow. We'll be talking about the PDFs in more detail tomorrow. So, okay, great. There was another question? Yes. How do they produce antiprotons? Yes, very good question. The antiprotons are produced by ramming the protons into a target and then collecting the antiprotons that come back out the other side. I know, it sounds a little bit inefficient, doesn't it? So how does this work? This only works if you have a very, very intense beam of protons that can be put on that target, and if you're able to somehow collect, sweep up, and keep stashed away the antiprotons that you already made. So in fact, you can see this is what this accumulation rate is. So it means that you're able to produce 3 times 10 to the 10 per hour off of that target. But I say that there are 3 times 10 to the 12 in the beam. So how's that happen? So Fermilab Tevatron has an accumulator where the antiprotons are stored before they get injected into the Tevatron. And that's where the accumulation happens. So it happens over a long period of time. And these are the rates that have been achieved so far. Okay, let me move on then. So before we get to the answer about the magnet, I just want to show you the outcome of all of these designs. So the outcome of the designs is that you can use the existing tunnel that's at CERN for the old LEP tunnel and put the LHC inside that with a beam energy of 7 TeV, ultimate beam energy of 7 TeV. By the way, this is the tunnel that's 27 kilometers in circumference. You'll read that distance all the time. But as important is that it's fed by this ring, the SPS, which has a beam energy of 450 GeV. So this is amazing. This 450 GeV proton synchrotron was the state of the art when it was built and when experiments were done there. And now it's being used as the front step or the front porch for the protons to sit at 450 GeV, be injected into the LHC. And so what has to happen in injection is the B field for those magnets is set as low as is necessary to accept those protons at 450 GeV. Then once they're in the machine and circulating at 450 GeV, then the B fields for all the dipoles can be ramped up until you get the 7 TeV beam. So it's important to match up the energies of these 2 rings in order to get a smooth transfer between the 2. And we'll see not only the energies, but also the RF frequencies of the 2. We'll see that in just a second. This is the rest of the complex too. The whole thing starts out with a little bottle of hydrogen gas. That's where the protons come from, just at the LINAC there. There was a question up there? No? Okay. Okay, so now we come to the question. Now we've decided that we're going to use the LHC LEP ring to build a proton-proton collider to have beams of 7 TeV ultimately. And how can we do that? The best way to do it, you might say, would be to have 2 separate rings. And I could drive electromagnets, superconducting electromagnets in the 2 separate rings. And I could have dipoles pointing up in one ring and pointing down in the other ring. And I'd get counter-rotating beams. And then maybe I could make some places where they come together, some vacuum chambers where the two rings come together and have interactions between the 2 beams. The problem is that if you're using this ring that the LEP machine was in, that tunnel is not big enough to put 2 rings inside. So what was decided instead was to take a design that puts both beams, both proton beams, in the same cryostat. So technically, they're different magnetic fields. You can see the two bores here and here, right here and right here. So those are where the two beams are. But the magnetic field is such that it's pointing up in one bore and down in the other bore. Okay. And so you really have two rings that are in the same cryostat, which is nice because then you have less to cool. You cool everything together in one cryostat with your liquid helium that we'll talk about in a second. And yeah, you save space. So you still have space for people to walk around and get to the tunnel. This was actually originally proposed as a cost-saving measure, and then they realized that, yeah, it was a good idea. It not only saves some money, but it saves space in the ring, too. So the Tevatron, by the way, is one ring because it's proton, anti-proton. And other proton-proton colliders have been two rings historically. Okay. Now, some of you may have heard about the LHC running at the reduced energy, and one of the main reasons for this is for safety reasons. So if you calculate what's the amount of energy that's stored in these magnets, here I've given you the inductance and I've given you the current that's in each one of these superconducting magnets. You can see that there is an enormous amount of energy. Multiply this by 1,200 dipoles. This 6.9 megajoules in each magnet times 1,200. It turns out that the total stored energy in the LHC magnets is on the order of a gigajoule, 600 megajoules, something like that. Okay. So all that energy is stored, and if something happens, if the magnets, for example, cease to become superconducting, all those currents have to go somewhere. All that energy has to go somewhere. How do you make sure that it goes out in a nice way instead of an explosive, uncontrolled way? So the way that that's done is that, well, first of all, the magnets are superconducting as long as the helium inside is superfluid. Why is the superfluid helium? So it's superfluid for a bunch of reasons. One is that the superfluid helium we know has very good heat capacity, the best heat capacity of any material. It provides the superconducting temperatures that's needed for these magnets. And also, since it's a superfluid, it can get into all the nooks and crannies of these cables through the cryostat. That's the property of superfluid, that it's a very low viscosity. The superfluid helium is even colder than it has to be for two reasons. One is that this is the temperature, 1.9 K, where the thermal conductivity is maximized. It actually turns out that there's the maximum there at 1.9 K. And it turns out happily that then you also have some safety margin, that you aren't operating right at the boiling point of the helium, but you have a good safety margin not only for the helium and also for the superconducting critical temperature. So it actually works out very well that way. Okay, what do you do if something happens? If something happens, the way that it's planned to deal with what's called the quench, if it's a problem with the critical temperature or the critical field, usually it's the critical field in the case of these magnets. So that means that the field gets too high above what's able to maintain, what the magnet's able to maintain for a current, for the field. The plan is to trigger some heaters that are on the magnet that will force the whole magnet to go non-superconducting, just regular conducting, and to somehow shunt all the energy off through a protection system. So in other words, it will just dump straight to the ground. And you know that this has been tested at least once in the LHC. All right, but this is really the reason. I just saw the feedback from the machine operators today, and they said that the reason that they're playing things safe is just the sheer amount of energy in the machine is a little bit something to be leery of, something to be careful of. And so before ramping up the energies and the luminosities and the beam intensities, they want to make absolutely sure that everything, all the interlock systems and protection systems are behaving as they should. Okay, great. Let me say a little bit about the beam current itself. I told you that there was something like 3 times 10 to the, anybody remember the number? 3 times 10 to the 14 protons per beam. But these protons are not spread uniformly throughout the beam necessarily. Okay? And the reason is this. Remember how I was talking about the RF acceleration being at a certain frequency? Let's talk a little bit more about what exactly that means. So the RF, the radio frequency acceleration, comes in on a wave like this, and the particles as they come in might be distributed uniformly. So think about the particles being in the beam as they enter this cavity where there's an RF field being applied. So what might happen is you might have particles that are here, and particles that are here, and particles that are here, kind of spaced out in Z. Let's think about this as being spaced out in Z. Okay. So if it turns out, actually I shouldn't say it's in Z, it's basically in the phase of the RF frequency, the radio frequency. Okay. The radio frequency is set up to give you a certain rho, a certain radius of curvature, right? That's what the acceleration gradient, the cavity, is supposed to do. If it turns out that there's a particle that's a little bit behind the other particles in the phase of the RF, what happens is that it doesn't get kicked out, doesn't get as much of an accelerating force, okay? It actually, am I saying this right? Oh, I see. It's backwards because I drew it backwards from the diagram there. Let me redo this and draw this on the diagram here. Okay. Just so everything makes sense there. Okay. So if you have a particle that arrives a little bit early, which is this particle here, so that's the particle D that we have up there. So what happens is if you have that particle come a little bit early, then it gets a little bit more energy from the RF system, so it gets accelerated a little bit more than its sister particle here at E. So what will happen is since D has a larger force, well, larger acceleration being applied to it, it will go off on a slightly larger rho, slightly larger orbit than the particle at E will. So if I were to draw it down here, if this is the nominal orbit that you would have, E follows this orbit, E follows this orbit. D would end up following a little bit larger orbit. It would loop out here. D loops a little bit out there. And this other particle, which up there on the diagram is F, since it doesn't receive as much of a kick, it follows a smaller radius of curvature and has a smaller orbit. So what ends up happening is that F, because it follows a smaller orbit, ends up on the next pass coming back to where E is, okay, because it takes less time to go on that orbit. So instead of being behind, it now gets on the same phase. And D, which was a little bit ahead, has to take a longer path, so it falls back a little bit in phase back to where E is. So there's this kind of feedback mechanism, at least in the longitudinal direction, to make sure that all the protons, in this case, all the charged particles, the protons, are being concentrated at certain points on the RF structure. And in fact, the way that these Ds and these Fs might move a little bit forward or a little bit behind is what we call the synchrotron oscillations. Synchrotron oscillations. So we have a little bit of oscillation in this longitudinal direction as the particles are being accelerated around. I think you can also see that the particles would tend to bunch up at certain points in the RF spectrum because of this sort of feedback mechanism. So in other words, the particles are not likely to be here or likely to be here. They tend to concentrate then at certain parts of the RF structure. Now, each one of these parts of the RF structure where the particles could be is called a bucket. It's a bucket in the RF frequency. And the machine precision is such that the operators can place the protons in certain buckets of the RF frequency, of the RF structure. And these buckets that are filled with protons are said to have the bunches of protons inside them. Okay. So instead of being 3 times 10 to the 14 protons that are all spread throughout the machine, they're actually concentrated then in a set of bunches. At the full design capability of LHC, we expect to have 2,800 bunches. Okay. Now, let me ask you a question about the bunches. So let's say that I have a bunch here, and a bunch here, And maybe I have other bunches behind it that are all moving in these directions. Let's say these are moving like this, and these are moving like this. So I have protons that are inside these bunches here. And I hope you realize that the congregation of these protons here is really, they're not really bunched quite like that. They're actually bunched longitudinally in this case, okay? But the question is, what should the rate be of these, of the collisions between these particles? Now, well, there you have the answer up there. The thing is that if you have NP, number of protons in the bunch, per bunch, for both this bunch and this bunch, then the probability to have some interaction between the two will be however many I have here. It can interact, each one of these can interact with any of the bunches over here, so that gives me an NP squared for the rate term. And then the more bunches I have, assuming that NP stays the same, the more chances I have to have a collision, because these two might collide this time around, and then these two will also come and collide, okay? So that's why that one is just a single factor of the number of bunches there. So when I talk about some total number of protons that are in the beam, that total number of protons is actually the number of protons in each bunch times the number of bunches. And so you can see that in order to increase the rate of collisions that you would have, the best thing you could do is maximize the number of protons that are in each bunch. But we'll see again that there are limitations about how many protons you can pack into each one of these bunches. Okay. Are there any questions about that? Great. Okay. So someone asked the question about how big the beams are. Question?
So why cannot the first bunch collide with the second bunch on the right?
That's a great question. In fact, maybe it does. The first bunch and the second, the question was why this bunch here might not collide with this bunch here. The answer is that if you just shot the two beams through each other like this, then they would. Now, you would only like to have the beams interact, the bunches interact in the middle of your experiments. You would hate to have precious Higgses being produced somewhere where you don't have an experiment. So what's done is to actually only bring the beams together at these interaction points. So in other words, they're kept apart carefully until they get to the interaction points, and then they're brought together. That's a great question. And then how they're brought together is another accelerator design.
LHC, right? Because we got two, basically, two rings, if I could say, where proportionally more, correct?
Actually, the other accelerators also have little bumps. They call them bumps in the orbit that keep them apart until they come into the collision. So even though you might be in the same magnet, you could still have rings that were maybe, that you can still separate the beams and still get the same bending. I mean, one thing you might think about is whether you had, if you could have something like this. I guess that's a bad example. Let me say instead, what if you had the beams that were somehow oscillating in and out like this around the ring, okay? I know it's a bad picture, but I could have other rings going the other direction, or other beams going the other direction like that. So then you have many interaction points that might be possible, but then you might employ some electrostatic separators to keep them from interacting at all those interaction points except the ones that you want. Okay, so if you hear people talking about orbit bumps or things like that, that's what's happening there. Okay, let's talk about the beam size. So there is a limitation to the beam size. In general, you'd like the beam size to be as small as possible, but the question is what's possible. So the beam size, when you hear people talk about beam size, you'll often hear them talk about two things, the emittance, and the emittance is basically a measurement of what's the spread and momentum of the particles. You can think about a longitudinal emittance, which tells you what's the spread and the longitudinal momentum of the particles. Or you can have a transverse emittance, which tells you, of course, what happens in the transverse x and y dimensions. Okay, the transverse emittance tells you what's happening with the beam width, as you can see up there. And the longitudinal emittance has to do with the bunch length. So the bunch can even be spread out within its RF bucket, or it can be very tight within its RF bucket. It can have a very short bunch inside that bucket. With the, oh, I see, I forgot to write the nominal LHC beam size. You'll actually see this in the next lecture, okay? But the nominal LHC beam size is on the order, at least in the transverse plane, of tens of microns. Okay, so pretty small. The bunch length is bigger than that, though. Okay, I'm actually going to skip the beta star here for a second. Let me get to the luminosity calculations itself. I told you that the rate was somehow proportional to the number of protons in each bunch squared times the number of bunches. Now, rate can be expressed in a bunch of ways. I mean, it's basically a per time sort of calculation, right, the rate. And if we go back to our idea of cross-sections, we can make a connection between the rate and the cross-section by being careful with the units as we have them. So I'm going to talk to you about the luminosity now, instantaneous luminosity, integrated luminosity, and the collision rates. Okay. So first of all, we're looking for something that's, we're trying to connect with this particle flow density that we had before. Remember, we had the particle flow density that I said was 10 to the 34 particles per centimeter squared per second. Remember that? So that has the right units, these units of area per time. So let me, well, actually, I guess you have them there. I'm going to write what Matt Strassler wrote this morning, or he wrote, that a barn here, same units that he had this morning, is 10 to the minus 24 centimeters squared. Turns out there are other units besides the barn, like the shed, but you'd have to be a very, very rare process to use the shed. And the barn and the shed were classified for a long time because they tell you something about the nuclear cross-section for interactions, and people had reason to classify that information. Okay, the L that we had, which is a rate, should be somehow in units of these number of bunches, the number of protons per bunch, you can see right there. So this L that we have, which is, after all, a rate, should be somehow in these units of per centimeter squared per second, right? So per area per time. And you can see some example L's up here. So a typical L for LHC, let's say that we have an L that's 10 to the 29 particles per centimeter squared per second. We can reinterpret that in terms of these different units. So microbarns, 0.1 microbarn, inverse, no, it should be 0.1 microbarn, not inverse microbarn. That's a mistake. So cross out that -1. Because the microbarn itself, oh no, actually, that's right. It's an area unit, okay, so per area per time. Okay, the reason that this is interesting is that you'll see, I think tomorrow, that the cross-sections that we'll talk about, the cross-sections have units that are in, as Matt said, barns or millibarns or femtobarns, if we're talking about very rare processes. So knowing what these rates, knowing what the processes are, and being able to calculate their cross-section using the techniques that you'll see here tomorrow, tells you what L you have to have in order to get a reasonable rate of these events happening. So let's say that you decided that you really needed to have one top quark pair produced every second at the LHC in order to do your measurements. So then you'd have to work backwards and say, I know what the cross-section of top is. It's a few hundred picobarns. And so therefore, I need to have something like 0.005 picobarn, inverse picobarn per second luminosity. And then you could calculate what that needs to be. So this is exactly what's been done, and that's how people arrived at that 10 to the 34 per centimeter squared per second number, by saying these are the processes we want to look for, the 1 TeV scale physics, the new physics that we're searching for. Let's try to figure out what the intensity should be. And I think you've seen today that the intensity is really a challenge. Okay. So besides this, which is a rate per area, we can also talk about a total number if we integrate up this value here. Yes?
Just need a little help. So
Uh-huh.
L is a fixed parameter for the collider at a given zone?
It doesn't have to be. So L, we can choose what we want L to be. And if you go back, you can see that one way to change it is just by changing the intensity of the beams, changing that NP.
And the area is area of the protons in some sense?
The area here, you mean compared to cross-sections with units of area? So the original idea of the cross-section has the geometric cross-section, right, the effective area. So if you like, you can think of it that way. So it's no coincidence that the 30 millibarns that Matt Strassler was talking about this morning corresponds to the geometric area of the proton. In fact, that's one of our models for trying to understand proton-proton collisions. Just treat them as geometric fuzzballs of gluons that might interact. Okay. Right. Okay, so that L sigma gives you a rate. What if you want to know the absolute number of top quarks that you will collect? Well, if you integrate up this rate luminosity over some time, then of course you should get something that has units of inverse area. And this is called the integrated luminosity. So it's integrated over time specifically. We don't want to integrate over area. Actually, it wouldn't make any sense to do that because when we have this integrated luminosity that has units of inverse area and we multiply it by the cross-section, which has units of area, then we get a dimensionless quantity, which is the number of interactions that have happened or that will happen or that we hope to happen. Okay. So if you can calculate what the sigma is, then you can get some idea about what amount of data is needed in order to give you a certain number of events at that process. So the example here would be the Higgs production cross-section, which is 32 picobarns total at a center of mass energy of 7 TeV. And you can compare this against what's been delivered to ATLAS so far. So delivered to ATLAS has been 20 inverse nanobarns times the 32 picobarns. And so you could try to calculate how many Higgses have been produced so far in ATLAS. Basically, should be less than 1 for sure, right? Let's see. Actually, a nano to pico. Actually, I get something like 0.5, huh? Maybe something's wrong with my calculation. Now, the key here is that these, have I done something wrong? 20 times 32 gives me 640, but then I have a factor of 1,000 converting between the nano and the pico. Nano's 9, pico's 12. Think it's right? Seems awful high. Seems awful surprising. So you got to find them exactly. So I think that we'll talk about this in on Thursday probably, Thursday or Friday. I said that that's the total amount. That's the total number of Higgses that are produced. But you saw that from what Matt was saying this morning, that if you make a Higgs that's decaying in the BB bar channel, that's very hard to find that. Practically impossible to find that because it's so much, it's the 1 in, what do we say, 1 in 10 to the 12 compared to the BB bar production that's happening all the time. Okay. Okay, thanks, Matt. Okay, great. That's scant consolation, I guess, huh? So, in fact, even though you might have them being produced in some channel, they're not in the channel where you can see them. So that's the problem. Okay. So I'm just going to put this slide up there, and you can look at this in the notes. Basically, this is what we can expect, or what we might expect for the total amount of data that will be collected by these LHC experiments. So keep in mind that we just talked about inverse nanobarn here, and what I have on this sheet here is inverse femtobarn. So that's a factor of a million right there, right? Yep. Yep, question.
What the biggest comparison of how much data was maybe collected?
Great question. So Tevatron, the total is right around 8 inverse femtobarns right now. Okay, so you can see that it will be something like 2013 before the LHC gets that much data. Okay. But what it means is that if you come up with a model that has a cross-section of a femtobarn, don't despair, because there will be a lot of data at the LHC. So there's a chance still to discover those very, very rare processes. And in fact, that's the whole reason for having that very high luminosity. Okay, I think that I should probably stop there, but let me just say one more thing. The limitations that we have at high luminosity, because this was a question from before, that you can't just pump more protons into each beam. Why not? The problem is that the protons themselves have electromagnetic interactions between the beams. So between the beams, whenever the beams are close enough together to affect each other. It's true that whenever they're inside the magnets being bent, they're well separated by the dipole magnet and the septum that's in between them where there's no field. But when they come close together, there's a beam-beam interaction that can happen. And this beam-beam interaction can throw off the orbits, the tune, if you like, I've written here, between the two beams. And that means that the protons can't be packed too tightly. Their emittance can't be too small. Remember, emittance was a measure of the spread of the protons inside the bunches. So the emittance can't be too small, otherwise they would form some very strong coherent beam-beam interaction against the other beam. Okay? So the emittance can't be too small. You can't push too much together. And the other thing that limits it is that inside the pipe where the beams are circulating, there's yet another smaller pipe inside that basically absorbs some of the halo particles, the flyaway particles, before they get to the cryogenic system and heat up the magnets. So that so-called beam screen actually has an aperture that's right there, 3.5 by 4 centimeters. So not a big aperture that these beams are going through. And in order to have some safe operation, you'd like that aperture to be well away, the walls of that aperture to be well away from the beams. So it means that you would like the beams to not have a width that will ever let them get close to the walls of the screen. I'm say it a little different way here. So if this is our aperture here, and the beam is here, the beam width, or if this is the beam width, you would not like to have any fraction of particles or any significant possibility for particles to get out to reach the edge here. So the sigma there is somehow a measure of the width of the beam. You'd like to be at least 10 beam widths away to the wall. Okay? So that also sets a limit on how big your emittance can be. If your emittance is very big, remember the longitudinal emittance I said was some measure of the beam width itself. So in order to keep the beam small, you want the emittance to not be too big. Okay, so we're bounded. We can't have the emittance be too small, but we can't have it be too big either. So that kind of sets what the bunch intensity can be, because the bunch intensity still has to let us have a certain number of collisions in the machine. So we want to keep a bunch density that lets us have a certain intensity of beams, this 3 times 10 to the 14 protons per beam. But we have to be careful about how we manage exactly what happens there. Okay, so that's the limitation that we have for LHC. If there are there any other questions? I'll give people a chance to ask any questions about that. We'll be talking about the experiments tomorrow. So this is the last chance, if you want, to talk about the LHC. But I'll be around all week so people can ask me more about that. Okay? Yes, Matt? There's a question.
You said the best we can get with these superconducting accelerators is 30 megavolts per meter. Do these plasma wake field accelerators do that?
That's a fantastic question. So the plasma wake field accelerators, the question was, what is the future for the plasma wake field accelerators? How do they compare to the quoted 30 megavolts per meter? So as I recall, I'm trying to remember. I think that the plasma wake field accelerator result that I saw was 3.3 megavolts per centimeter. Okay, so that has promise. There's work, but I think this was only a centimeter long, basically.
Yeah, and they
Right.
lose like 90% of the beam.
Right, so it wasn't accelerating the whole bunch uniformly. So the plans are to build a longer version of this, and I can't remember if it's 10 centimeters or 20 centimeters, to prove that this thing will scale, this gradient will scale over a longer distance. But it's very interesting. You hear people talk about tabletop experiments for particle physics. I think that we may have tabletop accelerators someday, but for reasons we'll see in the next lecture, the experiments will still be the same size. It has everything to do with how well you can bend the particles that are coming out. Okay. So what we really need are better magnets, higher field magnets. So if there's any possibility of people contributing to that, that would be great too. Okay, that's a great question. So we'll talk more about those detectors next time. Okay, thank you.
So let me just say
Oh,
real
Matt,
quick,
sorry.